the solid or cell itself. That's right. You utilize separation, you get the cell, and if the product is in the cell, right? For example, like protein, like lipid, something like this, amino acid. That's right. When you grow or when you culture the microorganism, and then microorganism it grows to a big size, and then also the biomolecule that include in the microorganism. But we need to this microorganism release the protein, release the enzyme, release the lipid is our product. The first step for this case that after you separate the solid by centrifugation, by filtration, the next step you have to break. That's right. You have to break the cell, and then it will release our product out of the cell. That's why we call this technique is cell disruption ก็คือทำให้เซลล์แตกนั่นเอง I will present this now. Sorry. of you can see my slide, that's right. When you can see my slide, okay. If you cannot see my slide, please talk to me. Okay, I will start to the cell disruption. That's I talked to you previously that if the product is intracellular product. I talked to you we have at least three kind of product. That's intracellular product, extracellular product, and the mass itself. That's right. For extracellular product, after the microorganism growth, and then microorganism will produce some product out of the cell. For that case, you separate solid and then you separate the liquid for the further technique. I will talk to you later. And another technique, cell itself is the product. Like we would like to produce bread, yeast. That's right. The yeast, something like that. And the last one is intracellular product. Intracellular product means product is in the cell. That's right. After the cell grows, it goes to a big size. We have to release our product from the cell. The best technique we call this is the disruption. We have to break the cell. That's right. And then the cell will release some product. That's right. Release some product out of the cell, and then we can separate further by centrifugation or by filtration. Next step. Okay. For this case, we have a lot of kind of technique to breaking the cell, to break the cell. Right. What sometimes we call disruption or lysing cell, that's right, or tissue. We have at least two techniques, like by chemical and physical method. As for this table, show you example of the cell disintegration, cell disruption technique. That's right. We have for the first, I will show you a chemical technique. The first step, we call osmotic shock. For this case, we have to add some water or add some solvent into the cell. If we add some water into the cell, that's right, that sometimes the cell will be a bigger size, and then until it larger, that's right, it larger. ก็คือใส่เข้าไปแล้วมันก็บวมขึ้น the cell will swelling and larger some chemical, some product out of the cell. That's right. This technique quite. That's why the condition is gentle. That's why the condition is gentle, and the cost of the equipment quite cheap. That's why. For this case, for example, we would like to rupture for the red cell. And another technique, we call it enzyme digestion. Enzyme digestion. For this case, we add some enzyme, that's right, to break the cell wall. That's right, to break the cell wall. For this case, the condition is gentle. The condition is gentle, but the cost is expensive. Why it's expensive? Because expensive due to enzyme. Enzyme is expensive. But for this case, is quite high efficiency because enzyme is specific to the cell wall. For the disruption, the first technique, you have to break the cell wall. You have to break the membrane. But enzyme is specific for some membrane kind for the cell wall. Okay, it's quite efficiency but quite expensive. Expensive because enzyme is expensive. And the next technique, we can breaking or destroy the cell wall by solubilization. We can you have destroy or dissolve the cell wall by some detergent. You have to add some detergent. You have to add some detergent. If you know, right, the detergent, mostly detergent, we have to part hydrophobic and hydrophilic part. That's right. Hydrophobic and hydrophilic. Hydrophobic ก็คือไม่ชอบน้ำ philic ก็คือชอบน้ำ That's right. We have two parts of the detergent. That's right. Tail and head. That's right. I will talk to you later. It's also the gentle condition, but the cost is moderate. That's right. It's moderate. It's not cheap. It's not expensive. Moderate. Right. For this case, for example, right, we buy salt acting on E. coli, for example. And the next example, right, lipid dissolution. Lipid dissolution, that means we add some solvent to destroy the cell wall. For this case, we destroy the lipid in the cell wall or the membrane. If the lipid is destroyed, okay, some membrane is break and then the cell can release some product of the cell. It is also the condition is moderate and cheap, like we add the toluene disrupt obliges. For this case, it's cheap, but how about the environmental due to the toluene? Toluene is the carcinogenic chemical. That's why it's สารก่อมะเร็ง. That's why it's a chemical problem also for this case. And the next technique, we can destroy the lipid by alkaline. We use the alkaline to destroy the lipid membrane also. For this case, the condition is high. Right? It's quite alkaline and organic solvent. The alkaline the condition is high. Maybe is destroy the nature some protein or some product inside, but the cost is low. That's right. It's cheaper. For example, we would like to extract the nucleic acid. Okay. This is the 5 example about the cell disruption by chemical technique. And the next one is the most used in the industry. We call it the mechanical. Mechanical, we use the force. That's right. Homogenizer, we use the blade or petal. We have some blade, คือใบมีด or petal to cut off the cell. We use the blade to cut the cell or petal. That's right. In this case, the cost is moderate. The condition is moderate. That's right. We use this for destroy the animal cell, for example. And the next example we call is grinding. That's right. The grinding we rupture. We crushing the cell by ablation. That's right. It's the cheap technique, and then we can use destroy or disrupt the cell of yeast or enzyme. That's right. And another technique, we use the ultrasonic. That's right. We use the ultrasonic. For this case, it's quite expensive. That's right. Because the ultrasonic is quite expensive. And another technique, we use the pressure cell. Right. For this case, the cell will be broken by the shear force. Right. And we use this in the large scale in the industry. And the last one is ball mill. That's right. If you chemical engineering, we have the ball mill. We have the ball, and then any ball to contact with the cell. That's right. We add cell into the mixture of the ball. Is maybe from stone or maybe from ceramic, something like this. When the cell and the ball contact together, that's right. And then you break the cell wall. Right. For this case, the condition is quite harsh or is high. That's right. It's strong condition. But the cost is quite low and most used in the large scale. For that case, the large scale cell disruption industry, we use like the pressure cell or ball mill in the most used for that case. Okay. For this example, we will show you the pressure cell and ball mill. Okay. For osmotic shock, I talked to you already, because osmotic shock, we add some solvent. In this case, solvent is the water. Some we add the solvent or the water into the cell. And then if a lot of water into the cell, and cell is bigger size, and finally it's break. And then we will release some product. some product out of the cell. That's right. Okay. For this case, we talk about the salt solution in the cell and salt solution out of the cell. Mostly the salt solution concentration of the cell is lower concentration compared inside the cell, because the outside the cell mostly is water. That's right. The concentration of it is lower. Okay. For this case, we talk about the osmotic pressure. Osmotic pressure is the flow of the solvent, or the flow of the concentration of the solution is lower. That's right. The lower side to the higher side, because this is the osmotic pressure. Okay, this was swelling some and then break the cell, and finally the cell release some product. Okay, for this case, we can relate it to the Van Hoff law. That's right, and be used to estimate this pressure which applied to ideal dilute solution. Okay, pi is the osmotic pressure on the P, equal to RT Ci minus CO. Ci is the concentration of the solute, or mostly we talk about the salt inside the cell, minus CO. CO is the concentration of solute or salt outside the cell. Mostly CO is zero. Why is zero? Because outside the cell is mostly the water, pure water. For pure water, the concentration of salt is zero. For this case, we mostly can assume it's zero for CO. Like for this example, we can use the Van Hoff relation to estimate the osmotic pressure across the membrane. Okay. Under the structure in 0.01 molar salt solution. And also we assume the internal salt concentration is 0.2 molar. And that's salt are fully dissociated. Okay, would you call this negligible, ordinary, or large pressure drop? The question is it the large pressure drop or lower pressure drop, or ordinary or moderate, something like that. And then you can calculate. For this case, mostly the cell disruption or bioprocess, we operate at about 30 or 28 degrees Celsius. For this example, I assume 28 Celsius. And then you can substitute temperature, RT, that's R is the gas constant. For this case, we should 82 cubic centimeter atm per gram mole per Kelvin. That's right. The temperature is 28, and then you convert from 28 degrees Celsius to Kelvin. That's right, to Kelvin. Okay. And then CI. CI is the concentration of salt inside the cell. For this case, it's 0.2 molar. That's right. And outside, for this case, we assume it's 0.01. It's maybe assume like zero. That's case mostly. Okay. How about 1,000 cubic centimeter per gram mole? What is this value? Side. That's what we check the units. That's right. And then finally we get like delta P is equal to 4.68 atm. That's right. 68 atm. Okay, this can, the pressure is quite high value. That's right, is what large pressure drop for across the membrane is to estimate the osmotic pressure. That's right, the osmotic pressure. Okay. For the osmotic shock, mostly we use the animal cell to quickly by rapid transition to the distilled water. And for the bacteria or plant cell, well, because this is quite strong, as like bacteria or plant cell is quite strong cell wall, it's hard to sit by osmotic pressure. It's maybe use another technique, like maybe chemical agent or like the detergent, like enzyme or solvent, or the mechanical technique. But the osmotic shock is better for most animal cell, like for larger cell. But for bacteria or plant cell, it's not best for the osmotic shock. You have to use another technique. You have to use like the chemical to dissolve the cell, or the mechanical technique is better for the plants or bacteria cell. Okay. Or another technique, you can use the detergent to dissolve right, the cell wall. As I talked to you earlier, the detergent we have two portions. The first portion is the hydrophilic and hydrophobic. That's right, hydrophilic and hydrophobic. Hydrophilic means the part that cannot dissolve with water. That's right. And hydrophilic, that's right, is the part that can dissolve in water. For this case, more like the hydrophilic portion is the ionic, that's an ionic compound, and a hydrophobic part or hydrophobic, is going to is hydrocarbon. That's for this I show you example of the detergent. This non-ionic detergent. For the non-ionic detergent can be used to break the plasma membrane and are commonly used to break the culture animal cell. For it's more preferred for like animal cell or the plasma membrane. For the non-ionic detergent, I use because they are phthalate enabling for protein. We use non-ionic because it cannot be denatured the protein and another biological compound. If you use like the ionic, like cast ionic or anionic, it may be denature the protein. For that case, this is we use the non-ionic. It's better than like anionic or cationic because it may be our protein activity, our enzyme activity, because it's soft condition. That's right, it's soft condition. And another one example is solvent. That's right. We can use like the technique of some solvent. That's right. Mostly we use like toluene, acetone. That's right, to break the cell wall. That's right. We use this to break like eukaryotic cell, something like it. We can use toluene, has been used to break the cell of yeast. That's right. But mostly we use this. It's not commonly used in the industrial scale, but you cannot break, but it's partially break. It's not full breaking the cell. And another example, like acetone, is often used in the preparation of biochemical from animal tissue homogeneous. We dissolve the cell membrane by cell membrane using the acetone, and then release the fat or lipid. Okay. Another one is a bioproduct that is extracted from cell with acetone and then precipitate is called acetone powder after drying. Okay. For this case, if you use acetone to break the cell, and maybe it induce the precipitate, some solid, that's right, precipitate from the cell by acetone also. You can break the cell and then you can precipitate out of the product from the solution also, this technique. That's right. This is I give you some shortly about the solvent, detergent, and aromatic shop. And the last technique that we mostly use in industrial, we call it is the homogenization, homogenizer. That's right. Would be the mechanical technique. That's right. The mechanical technique we use the force. That's right. We use the force to break the cell. Mostly we use the ball mill. We use the blade to cut the cell. We use the ball mill to contact between cell and wall. I think under it break. That's right. We have so sonication. We use the ultrasonic. That's right. Wave, something like that. Or we use the ball mill. We use the partial homogenization. That's right. Partial homogenization is look like the piston that move up to contact with the cell. That's right. And reciprocating milling. Reciprocating milling is like you move up, move down with the reciprocating. That's right. It's not continuous for that case. For that case, for example, like the first one is the hand operated or motor driving pressure. We have some pressure like this. We have the cell, and you can move up move down. That's right. For example, we have the cell like this. You move up and move down to contact with the cell, and then cell will break. And the second one, this is we have like this. This is like the impeller. That's not impeller. It's the blade. That's right. You move the blade in the rotate the blade. You have the cell. That's right. And it's break the cell. And it we use the what is this ultrasonic. That's that you use the ultrasonic, and the ultrasonic will break the cell also. That's right. For this case, we use the vibration glass bead. We have the glass bead inside this reactor, and then we vibrate. ก็คือสั่นสะเทือน we vibrate. And the last one is we use the pressure cell. We use the shear state. I will show the more detail in the next slide. That's right. Mostly the mechanical system, we can use the contact. That's right. The contact between the blade with the cell, the contact between the pattern with the cell. That's right. Or the contact between the mill or the bond mill with the cell. And also we can use the ultrasonic. Okay. Okay. The most use of the homogenizer. เจนจุธามีเรียนก็ไปได้เนาะเดี๋ยวอาจารย์อัดวิดีโอไว้อยู่แล้วนะครับเดี๋ยวค่อยดูวิดีโอก็ได้เดี๋ยวอาจารย์อาจจะพูดให้เสร็จอีกประมาณสัก10-20 นาทีนะครับ Okay, this is the most common use for the cell disruption. We call homogenizer. That's right. We call homogenizer. It's maybe we have for this case. You can look at this. Right. For this case, is it the area that the cell is contact with the. That's right. We have this part. That's right. We have A is we have to choose A is the hand wheel. You have to rotate this. Spring. If you rotate this, you have to add some feed to this direction. That's right. This is the cell will be contact between this valve and this, and then the cell will release. That's right. Okay. And be it the spring, right? Spring is driving. That's right. C is valve. This valve. This the area of the contact. Okay. D is another valve. That's right. In the pack ring. That's right, impact ring. You have to impact this mix together, and then some product is released. That's right. This is the homogenizer. You can rotate this, and spring will for in this direction or in this direction. If the spring is for the direction, we move this valve to contact with this. That's right. To contact with the valve says. That's right. And then the solid will break at this area. That's right. This is the mechanical and most used in the industrial scale. And this shows you the valve. To the object, you have to a lot of configuration of the valve. It's maybe like this is standard. That's why you do valve to contact with this. That's right. Or the valve is maybe some this or like this. That's right. This is the different design of the valve and this valve. That's right. Or break the cell. That's right. Okay. And this we can the mechanical disruptor or the efficiency is depend on n part ก็คือจำนวนรอบ That's right. When you pass the valve, that's right. It's maybe the first part is not all of the cell is not released or did not break. You have to add more one part. One part is what does it mean? That's right. If you rotate the A, that's right. It's move the valve to this and then move for this direction, and then you move in this direction is the first valve, and then you can rotate again to contact the second valve, the third valve, again, something like this. If you add more than cycle, okay, we will get the higher efficiency to break the cell. But the rate of cell disruption is depend on the cycle. The cycle. Okay, and then you can express the amount of the cell release. That's why we call X is the extent of disruption. extent of disruption ก็คือปริมาณที่ถูกทำให้แตกหรือปริมาณสารที่รีออกนะครับ usually depend on the pressure. That's right, on the pressure that's applied to the homogenizer, and also depend on the cycle or the end pass. That's right, end pass, and the K is the constant. A is also constant. This A is K and A is evaluate or estimate from the experimental result. And from the experimental result. Okay, for that case, mostly from the previous literature data, we know that the A for bacteria and yeast is between 0.9 to 2.9. That's right. It depends on the species. What is the species? It depends on the cell. What kind? Bacteria, yeast, fungi. That's right. It depends on the species, and also it depends on the culture condition. That's right. It depends on the culture condition, and also K depends on temperature. For that case, and then you can express X in terms of the R and ORM. That's right. X is R over RM. What is R and RM? RM is the maximum amount of protein. That's right. You have to know amount of protein in the solution or amount of product in the cell. That's right. It's the maximum concentration of protein or our product in the cell. That's right. R is the amount of protein released after end pass to the homogenizer. Rmax and R is the reality amount that released from the cell. Okay, and then can you express X as R over Rm, and then you can rearrange equation, you get log Rm over Rm minus R equal to KNPA. That's right. Please remember that A is a function of kind of the cell or the type of the cell. That's right. And also it's function of the culture media, but K is a function of temperature. Right. And also, for this case, you can calculate the energy required for cell disruption. For cell disruption, you can calculate the BEQ equal to QP. That's right, QP, and that's equal to QP is low CP delta T. That's right. The built-in energy for this case, Q is the flow rate of the suspension. P is pressure, low is density of liquid. CP is change capacity, and T is temperature. That's right. It may be like MCP delta T. That's right, MCP delta T. For Q low is M. That's right. Okay. And also, from previously we talked about the expression of constant of the release is the function of KNP is maybe like can like this, or example for E. coli bacteria. That's right. If there are some N is a function of something like N is power B. For previous that is N power B, but is function of B. Okay. B is really from the 0.3 to 0.9. It also depends on the cell type. That's right. It may be native or recombinant DNA concentration and growth rate, specific growth rate. Right. And the K and A depend on the type of the cell. I talked to you already. First case. This is for E. coli. This is for E. coli. We use this relationship. Okay. This is maybe the last. That's why we talk to the example. Right. In this case, we talk about the Micrococcus bacteria are disrupted at 5 degrees Celsius in homogenizer. That's right. The pressure operates at 200 and 550 kilogram per square centimeter. That's right. This is the limit of the pressure. The data for the protein release as a function of number of pass to the homogenizer are as follows. Okay. For this case, we vary the pressure drop 200, 300, 400, 500, and 550. And also the number of pass 1, 2, 3, 4, 5, 6. That's right. That's right. For example, right at 200, as pressure is 200, if you increase the number of pass or the cycle, that's right. You can, that's the percent of protein release will increase. It's common. That's right. If you add more than time, That's why the release of the protein release of our product is increased. That's why it's increased with the number of parts. And also if you constantly at constant N, that's why if you increase pressure, percent of protein release is also increased. That's right. It's from 5, that's right, 13, 23, 36, 42. That's right. For all this is increased. That is common sense. If you increase pressure, the breaking rate is increased. And also if you increase the number of parts or the cycle, breaking rate is also increased. That's right. This increase, this also increase. Okay, this is common. That's right. For this case, the question is how many parts are required to achieve 80% protein aside released at an operating pressure of 460 aside. For this case, for the experimental data, we have no 80% aside, and we have no the pressure for this. It's hard to interpolate or extrapolate from the table. But the best technique, you have to calculate equation like this. It's better, right? You have to calculate K, you have to calculate A because it's function of N and P already. The best technique, you have to calculate K and P from the experimental data, like the homework, like Percy present you. You have to plot some equation. That's right. Let's get I show you how to evaluate A and K. That's right. And then you can use this relationship to calculate after. Okay. For the first step, you can calculate term of we know like log Rm divided by Rm minus R equal to K N P power A. And then for this case, you can evaluate, right? For this case, we assume, right, the maximum is 100%, 100% protein. And then we can, Rm is 100 minus R over Rm multiplied 100. This is the same, right? The same technique. Rm is 100. Okay, this 100 minus R is the same. And then it's also is 100 minus percent protein release. Because for this example, we give you right percent protein release. This is a percent protein release. And the maximum is 100. Okay, it's common. Okay. In that case, we can follow right equation. This equation we plot Rm over Rm minus R. That's right. P or N, something like this. Okay. The first step, you have to calculate Rm over Rm minus R for each pressure. And then the first step, you plot this Rm over Rm minus R versus N. That's right. If you work this versus N, and then you get the slope is Kp power A. This is our slope. Kp power A. For this is for its pressure different. Okay. After you plot, you get the slope at its pressure, you get Kp alpha. Kp alpha, and then you evaluate this. That's like Kp alpha equal to log K plus A log P. If you take log, that's right. This is Kp alpha. Okay, if you plot curve between log Kp alpha and log P, that's right. But take log for this case, we take log like this. I forgot it's truly. Sorry. This it should be log. If we take log Kp power A equal to log K plus A log P, the slope of this is A, and intercept is log K. If you put log Kp power A, that's right, and log P, that's right. This is we put in term of log scale already, that's right. This is the log scale. You only put the Kp power A and P for this case, that's right. Okay. If you don't like to plot like in the log scale, you have to take this value. You have to take this value and plot log Kp power A and log P. Up to you. That's right. Up to you. Okay. And then you plot the Kp A in log scale and P, you get the slope. is 2.37 and k is 1.17 multiplied 10 minus 7. And then you get a and k already. That's right. You get a and k, and then you get the equation like this. Log Rm divided by Rm minus R equal to this equation. You get R is a function of pressure and N. That's right. It's a function of pressure and N. And then you can use this equation to evaluate the R at any pressure at any cycle, because this problem we talk about the 80%. That's right. For 80%, we cannot find from this table. That's right. And this pressure is between 450. It may be around this. That's right. For this case, it's hard to interpolate. Okay, you can use this data to find A and K. And finally, you get like this equation. You can use the equation to calculate R. That's right. Okay. For 80% protein release, for 80%, you substitute 80. That's right. This 80. Okay, you get Rm divided by Rm minus R. Rm is 100. 100 minus 80. You get 100 divided by 20 is 5. That's right. This is log 5. Okay. And then for this case, you can calculate N. That's right. N is equal to log Rm divided by Rm minus R divided by this term. That's right. You substitute. This is 5. P is 440. You get N is 4.5. But this we have to draw up to 5. We have N equal to 5, but you can release 80% for that case. Okay. Okay. I will talk for the mechanical method by Lysit Bismuth. Again, for maybe I will talk to you and I will try to take the video clip for you later. Do you have any question for this? Do you have any question for the example? Okay. Today I will talk only like the homogenizer, and then I will take the video for you for the Bismuth and only a little bit on the extraction. I will put this on Friday or Thursday, and then I will give you some homework about 1 or 2 questions. That's right. And then on next Tuesday, I will assign some students to present like this today. Okay. Do you have any question? I will stop the class now. It's 1 hour. It's okay for the online class. Right? Hello? No question, right? Okay. If no question, that's right. I will take some video. That's right. I will take some video on the remaining